In this video, I will demonstrate the workings of a redesigned pesticide sampler and point out its benefits. The need for a redesign revealed itself after a 12-week endeavor with the current sampler design. The average sample collection success was typically less than 50%. When samples were collected, there was an uneven distribution of samples in each of the vials. Temperature violation of the samples occurred on days when air temperature rose above 25 degrees C, which meant that the samples we did collect were likely compromised. The sampler in its current form is very complex with many parts, and further attempts to rectify this design seem unpractical. So we felt it would be in our best interest to attempt a complete redesign, keeping things simple and starting with a sampler housing that would give us more flexibility for cooling options. Here is an overview of some of the challenges that we found with the sampler in its current design. Beginning with installations, the sampler in its current design must be deployed vertically. This proved to be challenging at some sites. Also, it must remain at a constant depth, meaning that it must rise and fall with the stage. And cooling required external power. This proved to be challenging at sites that did not have AC power. It typically took 7 to 8 deep cycle batteries to power the sampler for 1 week. Sampler collection. As previously mentioned, we had a poor success rate with collecting samples. The sampler also has a complex design, which is difficult to set up and deploy, and leaves a high potential for failure. Sampler cooling. The sampler was not originally designed to be cooled, making it nearly impossible to entirely insulate the outer portions of the sampler. Also, there is no provision to use ice to supplement cooling on the inside. Sampler deployment. It utilizes a cryptic user interface that requires one to look up a code and then enter that code on a dip switch on a handheld remote. That code is then confirmed using a flashing LED. After the sampler is activated, there is 2 minutes to deploy the sampler and get it into the stream. That's because the sampler must pressurize its line shortly after being installed. Also, there's the inability to test all the components with the pre-deployment setup. Sampler control system. If the electronics require any kind of modification or change, it must be shipped for modification and updates. Also, the user cannot change the program logic or verify time settings. Besides, the main benefits of a redesigned sampler is that for installations, we could deploy the sampler at any angle, and we have the potential to deploy the sampler at any depth. We also would have the option to use either ice or an electric cooler, or even both, to chill the samples. We would also have an easier to use interface, and by using a displacement-based sample collection system, we could collect samples more reliably and consistently. Let's start off with our sample controller. We have selected a sprinkler system timer because it suits our needs pretty well. This particular one can control up to 9 different zones. And for our application, that means that we can control up to 9 different sample extractors. Also, this particular timer gives us the ability to program each of these zones individually for the day. So, just for example here, I'll select zone 1. So that would control 1 sample extractor. We can select which days that we choose for it to collect samples, and also the number of times per day. We can select 1, 2, 3, or 4. This gives us a lot of flexibility. Now moving on to the actual control of the sample extractor, one of the disadvantages with using the sprinkler timer is that it's a 24-volt AC system, which means that the outputs for the controller are 24-volt AC, which makes it necessary for us to run this device in between the timer and the sample extractor. This device converts the 24-volt AC coming from the timer to 12-volt DC, which is what's needed to operate this 12-volt motor. Now let's take a look at the sample extractor. The sample extractor consists of a 12-volt DC motor that is tied to a threaded rod, and then the threaded rod goes through the top of the syringe. When the motor spins, the threaded rod will spin and then pull the plunger up through the syringe, thus extracting the sample. When 12 volts is applied to the motor, the rod spins at such a rate in which it draws about 4 milliliters every minute. Once we determine the type of syringe that we would use for this application, whether it be Teflon or not, we could then construct a cartridge in which we could easily slide the syringe in and out of, making it very easy to service and change in the field. Moving on to the housing, we have selected a cooler for this prototype. And in the cooler we have added a little bit of additional insulation, and we've also modified the lid with the cooler that we've previously used in the other sampler. For the sampler housing, we've put together a sampling insert. This will serve several purposes. Number one, it'll hold or contain the sample extractor. It'll provide a route for ducting for the cooling system, and also provide a barrier if we choose to use ice. So to give you an idea of how this works, I'll start here with the cooling unit. First of all, this particular cooling unit, the fan has been reversed, so it will draw air in from the sides and then blow the cold air down or up this direction. So when the ducting is inside the sampler, it would sit configured like this, and then the cold air would be forced from the cooler down to the bottom where there's some slits that will allow the cold air to come out. So I'll assemble this and just give you an idea of how this would work. The sleeve would just fit right into the sampler like so. And then we could place the sampler in the hole just like so. And then we'll grab the ducting, which will just go down through the center there. And then when you place the lid on, the cooler would center itself over the ducting work and then allow the cold air to flow down to the bottom. So here's an overview for the advantages of using this type of sampler. First of all, this sampler uses a displacement-based sample extraction system that will allow us to collect samples at any angle or any depth. We will also have an additional cooling option to use ice to either supplement and or replace the electric cooling system. Fewer sampler restrictions will allow for simpler and less expensive construction of field housings. The simple sampler design will allow units to be field serviceable. We will have a more comprehensive and simpler user interface. Fewer parts will be less expensive to build and operate. And the simplistic design should yield a higher potential for reliability.